Enantiotopic groups present the interesting situation of being one step removed from chirality. That is, if one of the enantiotopic groups were replaced with another group that's not present on that center, then we would generate a stereocenter. To the extent that we can actually use chemical reactions to replace or modify enantiotopic groups, thus it's very important to understand how the spatial differences between enantiotopic groups influence their reactivity, specifically their interactions with chiral compounds. For instance, in this example of the phosphorylation of glycerol, we see that glycerol is an achiral compound. It possesses a plane of symmetry, but that the two hydroxyl groups out here are enantiotopic. They're related by a plane of symmetry, and if you did the Q test, you would find that this central carbon becomes a stereocenter in the Q molecules, and the resulting Q molecules are enantiomeric. So the two hydroxyl groups are enantiotopic. In the presence of a chiral enzyme and a phosphorylating agent, ATP, we turn one of the hydroxyl groups into a phosphate group. In a sense, we've performed the Q test on this molecule by replacing one of the hydroxyl groups with a different group. But the interesting thing is that the enzyme is able to select one enantiotopic group over the other. As a result, we get only a single enantiomer of product out of this reaction. How is a chiral enzyme, or more generally a chiral object, able to distinguish enantiotopic groups? Well, in the last webcast, we saw how a chiral aldolase enzyme could distinguish the enantiotopic faces of a nucleophile and electrophile. Distinguishing enantiotopic groups follows the exact same principles. The interaction of one enantiotopic group with the chiral enzyme is different from the interaction of the other enantiotopic group with the enzyme. One has to be more favorable than the other. As a result of these different interactions, it's only favorable to react one of the enantiotopic groups and not the other. Here's another example where enantiotopic hydrogens are distinguished by a chiral enzyme. Alcohol dehydrogenase is able to convert the primary alcohol ethanol into acetaldehyde. It does this by removing a hydride and a proton, but interestingly, it only removes one of these enantiotopic protons. We know that because of the experiments described here below. If we replace one of the enantiotopic hydrogens with deuterium, then when we run the reaction, we see that deuterium is selectively removed, and hydrogen is left in the product. On the other hand, if we replace the other enantiotopic hydrogen with deuterium, run the reaction again using alcohol dehydrogenase, we see that deuterium is selectively incorporated into the product. So the proton or deuterium that's in the back is always the one that's retained in the product. What property of this specific position allows it to be distinguished by the chiral enzyme? A good way to think of it is the property of prochirality. Prochiral groups are one step away from chirality, and enantiotopic groups fit this bill perfectly. The sense of prochirality of one enantiotopic group versus another depends on the enantiomer that's formed upon replacement of that group, and this is how we name and distinguish prochiral groups in terms of nomenclature. So for instance, looking at the example here of enantiotopic hydrogens HA and HB, replacement of HA with a group of higher priority, such as D, will lead to one enantiomer of product. Replacement of HB with that same group will lead to the opposite enantiomer of product. And the hydrogen that leads to the R configuration is called the pro-R hydrogen. The hydrogen that upon replacement leads to the S configuration is called the pro-S hydrogen. And it's this property of prochirality, being one step away or one replacement away from being chiral, that allows us to distinguish the two hydrogens on spatial terms. We've already seen how enzymes and chiral objects can distinguish enantiotopic faces of molecules, but how do enzymes distinguish prochiral groups? Well, the ideas here are very similar. So any chiral object that approaches ethanol is going to have some ideal orientation for binding. So if you consider an enzyme with, say, a hydrogen bond acceptor here where I've drawn this black dot, the ideal orientation for the enzyme, if it's approaching the substrate from the front, as I've drawn here, is to have that hydrogen bonding acceptor on the right. That way, the OH group can hydrogen bond efficiently with that group. This leaves only the front hydrogen available to the enzyme for reaction, or more specifically in this case, removal, leaving HB behind on the product. Any other kind of approach of the enzyme, for instance, approach with the hydrogen bond acceptor on the opposite side, or approach of the enzyme from the back of ethanol to react with HB, will be less than ideal. In this way, the enzyme is able to selectively react with HA rather than HB. In a sense, you can think of HA and HB as groups residing on the enantiotopic faces of a plane that doesn't contain any atoms necessarily, but represents a plane of symmetry of the molecule. Thus, in a sense, the enzyme is distinguishing prochiral faces, and the faces it's distinguishing are those of the plane that interconverts the enantiotopic hydrogens HA and HB.